This is the first of a series of lectures on what's called extended formulations. So let's get to the basic question. The central question that we wish to study and provide machinery to study is the following. Given a polytope P in n dimensions with an exponential number of facets, and when I write that it has exponential number of facets, of course I mean that these can't be, that we need all of these for the description. So it's not so much a property of the representation, but an actual geometric property of the polytope. Can a polytope with exponential number of facets be described as the projection of an extended polytope with a small number of facets, namely a polynomial in n number of facets, as the projection, or really any affine map, of some polytope, which I'll typically call Q, in bigger dimensions, so n is typically going to be much bigger than little n, where Q has a polynomial number of n facets. Now this is important for us. We've seen a number of polytopes that have exponential number of facets. The R arborescence polytope has exponential number of facets. The non-bipartite matching polytope has exponential number of facets, and so on. One of the reasons that this is significant is that these extended formulations, as they're called, naturally interact extremely well with linear programming, because we can always just solve an LP over larger polytope. So the significance for linear programming is that if indeed if Q is an extended formulation of P, of our polytope P, and thus P is some affine map of Q, then we can always write our LP, minimize C transpose X, subject to X in P, as the problem of minimizing. Let me write this actually a little more explicitly. I think it'll be convenient. Let's even more say that P is some matrix applied, so just a linear map of Q. So in that case, then instead of minimize C transpose X, I can write this as minimize A transpose C transpose capital X, where capital X is now in the extended formulation. And my extended formulation is clearly, now I can solve that. In particular, if our polytope is defined by a small number of facets, then I can solve the separation problem very easily just by, given any point, I just look through all of them. And therefore, immediately by our work on the ellipsoid algorithm, we know that we can solve LPs of this form. One convenient form of representing this, we'll often write if P, and sorry to use A, again here I'm overloading A, this is obviously a different A. If P is all X such that AX is less than B, we'll often write a canonical extended formulation that looks the form Q is all XY such that BX plus cy is less than d. And in that case, the affine map from Q to P is just a coordinate projection, just keeping the first k coordinates. So what we're going to do in this lecture is start off with some good news and show that indeed this is possible. So I'm going to next write down a polytope which requires an exponential number of facets to describe in n dimensions, but which can be described as the projection of a polytope with order n squared, not exponential in n number of facets in order n squared dimensions. That's about what it will be. So this is the example of the Permutahedron. So let's first say what this is. So let's let Sn denote the permutations of the integers 1 to n. Then we're going to define the Permutahedron. I'll write it as P of n to remind us the ambient dimension. Perm. This is going to be the convex hull of n factorial extreme points, one corresponding to every single permutation of the vector 1, 2, 3, all the way up to n. So in other words, it'll be the convex hull of the points sigma 1, sigma 2, sigma n, where sigma is a permutation. So, for example, in 3 dimensions, the Permutahedron is equal to the convex hull of the vectors the vector 1, 2, 3, and all of its permutations. So 1, 2, 3, 2, 1, 3, 1, 3, 2, 2, 3, 1, 3, 1, 2, and 3, 2, 1. So now we'll give a representation of it in terms of its facets, and we'll see that it requires an exponential number of facets. So a claim, which by itself is interesting, is that the Permutahedron, rather than expressing it as the convex hull of n factorial extreme points, it's equal to x non-negative such that the sum of xi is equal to n plus 1 choose 2, and the sum for any subset S of xi is at least cardinality of S plus 1 choose 2. And this has to hold for every subset of 1 to n. It's easy to see that the Permutahedron is contained in this set, since every vertex clearly satisfies this, and therefore the convex hull, since all of these are linear constraints, the convex hull will satisfy all of these constraints. So we can check that that all of these constraints are satisfied. There's another way to write this down. So this is equal to x non-negative, such that I'll just write this first one a little bit more compactly, getting a little lazy here. X of n is equal to n plus 1 choose 2. And similarly, rather than write sum over s or sum over a subset x of I, I'll write x, and now I want another subset named t. Now this is less than or equal to n plus 1 choose 2 minus n minus cardinality of t plus 1 choose 2. You can easily see that these are equivalent, these formulations. And so again, the fact that the Permutahedron is contained in this is straightforward, as we argued. Now let's see why this is the case. So I want to argue this claim. It's actually, again, by itself interesting. And one thing that I want to note is that this has a particular form. The Permutahedron is a special case of a polytope called polymetroid. And these are polytopes that are defined. So a polymetroid is a polytope P that has the form x non-negative such that x of t is less than or equal to f of t for any t subset of 1 to n, where f of t is submodular. So to check that the Permutahedron is indeed of this form, we just need to check that this function is indeed submodular. And you can see that this right-hand side, well, this is a set function, so we can call this f of t. You can see that f of t only depends on the cardinality of t. So f of t is some scalar function of the cardinality of t. And just by multiplying this out, just by expanding the n choose k terms, you'll see that this is a concave function of the cardinality of t. And you can do this as an exercise. Any set function f that depends in a concave only on the cardinality of the set and in a concave way on the cardinality of the set is submodular. So polymetroids are a very rich topic that we're really not going to have time to cover in any depth. We're just focused on the Permutahedron, but it is a special case of this, so it's worth mentioning. All right, so here's an important property that we get by writing it in this second form. So for any polymetroid, so for any p that's again equal to what we just wrote, x of s less than or equal to f of s for any s subset of e, f submodular. For any vector that's non-negative, the problem that LP maximize C transpose X subject to X in P has a solution that we can write down explicitly. Has the following solution. So first, let's order the coordinates of the ground set 1 to E according to decreasing order of the coefficients of C. So order them so that C1 is bigger than C2, etc. is bigger than Cn, which remember is greater than or equal to 0. Then, and I'll leave this as an exercise, the optimal solution to the LP has a first coordinate that's equal to f of E1. Second coordinate, which is equal to f of E1, E2. Remember, f is our set function, so f of E1 is our set function evaluated on the set that contains only this first element. F of E1, E2 minus f of E1, and so on. The last coefficient will have value f of E1 to En minus f of E1 up to En minus 1. A few things of note here. First of all, if f is integer valued, if it's an integer valued submodular function, then this result shows that the solution to the LP for any non-negative C is going to be x star, which is going to be integral valued itself because f is integral valued. So this shows that P has all integral vertices. The first thing to note. And immediately that implies for us that we have the correct description of the Permutahedron. So for us, this allows us to conclude that the Permutahedron is indeed as given on the previous slide. So this tells us, and it's easy to check, that we can't eliminate any of these constraints. So this tells us that our Permutahedron requires exponentially many inequalities to define in its ambient dimension. In other words, if we look at the geometric shape, it's going to have an exponential number of facets. Again, that's a geometric property independent of how we choose to represent it. A second note that may be of interest to us, given our previous lectures on submodular functions, is that let's think about this function, I'll call it f hat of c, which is the value of the solution to this LP. And it's equal to max c transpose x subject to x in P. I'll leave this as an exercise for you to show that this is essentially the Lovász extension. This is the Lovász extension, taking values, for any c that's in 0, 1 to the e. So I'll leave this as an exercise for you to show. Okay, so now what we want to do is we have our example of our polytope that has exponentially many facets. The claim is that we can write this as the projection of a polytope in order n squared dimensions with just order n squared facets. So let's see how this works out. This links to another topic that's very near and dear to us from previous lectures in the series, from when we were talking about bipartite matchings. So given an element of, given a permutation, sigma, let's define a n by n matrix that's just the permutation matrix. So let y sigma be the n by n matrix of this permutation. In other words, the ij element of y sigma is just going to be 1 if j is equal to where the permutation sends I, and it's equal to 0 otherwise. Now it's easy to check that from y we can easily recover the vector x sigma. So in particular, x sigma, its ith coordinate is just given by summing from j equals 1 to n j times y sigma of I j. So we can always recover x from j. Now let's look at what is the convex combination of all y sigmas. Again, this is what we've already seen, what we've already characterized. The convex hull of all the y sigmas, where sigma is a permutation, is just given as y n by n matrices that are component-wise non-negative, such that yij's equal 1 for I equals 1 to n. And similarly, the sum from j equals 1 to n of yij is equal to 1. And this has to hold for every I and j. In other words, this is exactly the bipartite matching polytope on the complete n by n bipartite graph. This is exactly the bipartite matching polytope on the complete n by n bipartite graph. So that's pretty much the story. So let's wrap it up. We see that therefore the Permutahedron is all x such that there exists a y greater than 0 that belongs to the bipartite matching polytope. In other words, all x such that there exists a y greater than 0 with xi equal to the sum of j yij, j equals 1 to n, and y satisfying those two constraints. The sum over I of yij equals 1 for all j, and the sum over j of yij equals 1 for all I. So we have a total of n, capital N, would be n squared plus n dimensions. If I wanted to describe my extended polyhedron whose projection onto the first coordinates is equal to x, and n squared plus 3n constraints. So this is a nice example. It's a positive example of where this happens, and there are many other nice examples where we have a polytope that requires exponential, that has exponentially many facets, but can be written as the projection, of a polytope with a polynomial number of facets. In the next lectures in this sequence, we're going to start talking about polytopes that don't enjoy this property, and in particular that require an exponential number. We're going to be developing the tools and to establish that and giving some interesting examples. We'll pick this up then.